Okay, we're going to talk about fossils and what is the truth about fossils. More than anything else, fossils, and in particular, what kind of fossils are a big pro-evolutionary gimmick. I mean, gimmick's a good word, I don't know, for promoting evolution. Okay, does anybody know what fossil is on the, what that is? How many of you live around here? This is one of the most famous fossil finds of all. This is the Tyrannosaurus Rex Zoo that is now owned by the Chicago Field Museum of Natural History. Surely you've seen Sue. Okay, that's the T-Rex fossil. All right, so more than anything else, fossils, in particular dinosaur fossils, are a big deal, or a supposed big evidence for proving evolution and for proving that the Earth is 4.6 billion years old and that the dinosaurs lived 65 million years ago until they became extinct due to that meteor hit. Okay, so it's important for you to understand that fossils do not prove evolution. Well, everybody knows fossils have been dated, right? Well, let's talk about that. I brought with me something that I bought in Florida. Okay, this is a nautiloid fossil, and look, it has a nice little label on it. And the label says, fossil nautiloid, Devonian period, 360 MYA. What's MYA? So they say that these are shellfish, there's 4 of them on here, these nautiloids, this is the shell, that they lived 360 million years ago. How was that number? That's an absolute date. Remember, absolute dates assign a number to it, whereas relative dating just simply says this was younger or older, the older on the bottom, then the younger, and younger. So where did they get that absolute date? That sounds official, doesn't it? Anybody know how this was dated? Or let's say I find a fossil and I take it to a renowned geologist in Chicago and I ask them, I found this fossil. We're going to talk about this one a little bit. I found this fossil behind the Armacost house when they were digging the pool out the first time back in 1970, I'm not sure. Okay, 75, 76. So if I were to take my fossil to a geologist and ask him how old is this fossil, what would they do? Anybody know?
They would use an index fossil.
Exactly. Rocks and strata are dated by index fossils. So what happened with this nautiloid, did they radiometrically date this rock? No. Well, only igneous rocks can be radiometrically dated. What about carbon-14? Once living things can be carbon-14 dated, but this has been fossilized. Did they take a little sample from this rock and date it at 360 million years ago? You know how this date 360 million years ago was established? Somebody saw the nautiloids, got out a big compendium of all the index fossils, looked through it, and said, oh, this looks like this particular nautiloid species. Oh, they evolved 360 million years ago. Therefore, this fossil is 360 million years old. What is that? Correlation. They did assign an absolute date to it, but this was not radiometrically dated, and most people don't know that. So if I were to take my fossil that I found in 1970 something, I was a child, okay, and I were just going to take this to a geologist, what would they do? Exactly what John said. They'd look at the fossils on here, they're seashells, and this would be really hard to date. They're not going to try to radiometrically date it. They can't. This is limestone, okay? So I want you to understand that the absolute dating techniques of the radiometric dating techniques, they sound very scientific, they are used, but they're very limited in their use. Most rock dating is done through correlation. This rock has this fossil in it. All right, oh, and let's look around. Oh, there's an index fossil in this same layer. Look it up in the compendium. Okay, that's this particular species. A lot of them are trilobites. And they'll say, okay, this species evolved so many million years ago, therefore that rock is that date. So you need to understand that about fossils. It's not been proven that these rocks are millions of years old. It's not been proven that that nautiloid fossil is 360 million years old. It simply has not. So fossils, dinosaurs are a big pro-evolutionary scam. Okay, so let's talk about what are fossils. Okay, what are fossils? Let's do this. There we go. We have some root words. The root word for fossil comes from the Latin. There's a verb, the Latin verb to dig. There's a Latin adjective, fossilis, which means dug up. So quite literally, a fossil is something that was dug up. Okay? So on this picture, I've got this top corner fossil is from California. It's a velociraptor. It's on display at the University of California, Berkeley. And of course, the one in the middle there is from the Creation Museum's collection. So what are fossils? Of course, we have to have a definition. A fossil is, you see on the board the definition. I went too far. Let's go back. Fossils are the preserved remains of animals, plants, or other organisms. Even microorganisms have been fossilized. Okay, even very simple animals have been fossilized. So they are the preserved remains of animals, plants, or other organisms, the impression of living things, or even the traces of their activities. So a fossil can be the organism itself. Fossil can be a plant or animal, can even be a microorganism. Fossils can be just the impression, and fossils can even be a trace of animal activity, such as footprints and so forth. Okay, we even have fossilized dinosaur eggs. We have fossilized dinosaur footprints and so forth. Types of fossils. Types of fossils include true form. True form is when the actual organism itself fossilized. This nautiloid is a true form fossil because we have the entire shell of the nautilus. This is a true form fossil. Okay, true form fossil, the actual organism petrifies. Petrify, of course, means turn to rock. They also sometimes use the verb lithify, means turn to stone. Then we have mold cast fossils. This is an impression of an organism. That would be the mold. And then sometimes the mold will fill up. That would be called a cast. This fossil has a lot of casts and molds on it. Okay. So what a cast mold fossil is when you have an impression of the organism. That's the mold. And then sometimes the impression will actually fill up and form a cast, just as if somebody poured plaster Paris in a plastic mold and then you get a cast of some object. This is a similar idea. It's literally a cast. Then we have carbon residue fossils. This happens when a living organism is trapped between layers that are already solidifying and under pressure. Of course, the organism will be compressed and all that remains is a carbon film. This is a sandstone fossil from Lake Michigan. Oh, it must be millions and millions and millions of years old. And actually, you can see it's a carbon residue. It's got a very thin film, a part of the remains of that fish. This is an alewife, which is a common fish still living in Lake Michigan today. Okay? That's a carbon residue fossil. Then, let's talk about each of these. True form fossils. Both of these fossils are from the Creation Museum's collection. And you can see the entire shell of that crab has fossilized. And so is the gastropod. Both of those were found in France. There are 3 processes of true form fossilization: permineralization, replacement, and polymeration. There they are. We're going to talk about each one of them. And I'm going to explain a little bit to you of how fossils form, what's involved with it, what are some of the ways that fossils form. So if we have a true form fossil is when the organism itself, its entire shell or an entire bone, the actual object fossilizes through permineralization, through replacement, or through polymerization. Okay, let's look at permineralization. This is a trilobite fossil. Got it here. I will admit to having to buy this. I did not find it. This is a trilobite fossil. Trilobites are invertebrates. They're numerous, millions and millions of them have been fossilized. What happens in permineralization is we have a chemical reaction going on, and we have the infiltration of different kinds of minerals. This particular fossil has probably been infiltrated by hematite because of its black color. Probably other minerals as well, but this one has a lot of hematite in it, which is an iron mineral, and that's why it kind of appears to be black. So that is a true form fossil. We have the organism itself has petrified. This is a vertebrae from a bison from the Creation Museum's collection. This was also formed by permineralization. Bones. What do you know about bones? Bones have a very high mineral content already. Bones are primarily, the matrix of the bone is made up of a substance called calcium phosphate. Okay, and so that's why we have a lot of fossilized bones, because they already have a mineral content. This is calcite, is the name of the mineral. Calcite is a calcium mineral. Then we also have the process of replacement. What are these? What is this? Petrified wood. I have a little piece of petrified wood, okay, that I found. And this is a replacement where the wood cells have been replaced by minerals. In this case, the mineral silica, silicon dioxide, very common in the Earth's crust. So a petrified wood is another example of a true form fossil. And this forms through the process of replacement. Here's polymerization. Anybody recognize what this is a picture of? Amber. There's millions of insects, even spiders, and even small amphibians. There's even an amber sample that has a intact frog in it. Okay, this particular piece of amber, I got this picture off the internet, and the little tag next to it said fossilized amber 35 million years ago. Where did they get the 35 million? I don't know, but they didn't carbon date it. So what happens is resin from the tree sap, okay, especially your pine trees are very sappy, okay, and so insects become trapped in amber, and if the amber is properly buried quickly, it will fossilize, and we'll have the entire insect encased in amber and polymerizing. So this is the process of polymerization. Those are true form fossils where the organism itself or its shell or some of its skeleton has fossilized. Then we have the mold cast. There are three different kinds here. The first type of mold, this is only a mold. It was not filled in. This is simply the impression of the outside of a seashell. So this is an external mold. On my limestone here, I have several external molds. Here's one. So an external mold, we have an impression of the organism made in soft sediment. Then eventually that sediment is buried, or actually it has to be buried pretty quickly, or that impression will be worn away or washed away. That's a external mold. Cast. A cast is when the impression fills with minerals, and it is literally, the mold fills up and you have a cast of the original shape of the organism. This is, let's see if I can do this. This will give me a laser pointer. This, of course, is similar, these aren't sand dollars, but they are a marine invertebrate type of animal. And this is not the actual animal, it is a cast of it. Okay, so we have the cast is when the impression fills up. So here's my fossil. You can see on there we have several external molds or external impressions of seashells. Right there, there's two of them. There's a cast. The seashell's not there, the mold has been filled in. And then there's an internal mold where, that one's a little hard to see, where the inside soft parts have been fossilized. You can see it a little better on this side. Where, and on this one in particular, you can see where the soft muscle part of the shell is partially opened, and that has fossilized. Of course, that's a soft part, it won't fossilize, so that has to be an internal mold where what happens is you have an impression. And if it's an impression of the external surface of the organism, you will get an external cast. Okay, but if it's an impression inside, you will get an internal mold, and you'll see this better on the next illustration. So those are cast and mold type fossils. This one is from the Creation Museum's collection. This was a very nice fossil. Notice this is a mold of the external features of this leaf. Across from it, it was cast. There's a cast that was made out of the mold. You see that? So that is another example of an external mold that has been cast. This one is an example, also from the Creation Museum's collection. This one is an example of an internal mold. See it here? This is the internal part of the fish, and its internal structure actually is cast because the inside of that fish filled with minerals. So that is another example of a mold cast type fossil. Okay. The last type of fossil is the carbon residue. This is from the Creation Museum, and what happens is a carbon film. Of course, living things are made of carbon. Elementally speaking, living things are primarily carbon. And so after we have compaction, gases and water will distill off and only the carbon remains. Most of your leaf fossils are carbon residue, and the fish fossil that I showed you is a carbon residue fossil. So you have distillation, and then the water and other materials distill off, and all you have left is a carbon film in the shape of the original organism. That's a carbon residue fossil. And of course, this requires high pressure. All right, so you see we've talked about the fossilization processes, three of the main ones: permineralization, replacement, and polymerization. So I want to review general steps for fossil formation. This is what you need to know and remember. In general, the first thing that must occur is rapid burial in sediment of some type. It can be sandy or silty, it can be clay, it can be mud. We have to have rapid burial. Then we will have petrification, turning to rock, solidifying. There's various processes. They can involve the permineralization, chemical processes. They can involve the mineral replacement, like petrified wood, or we won't have any of those. We'll have the fossil trapped in amber, and it will polymerize so that the actual insects inside the amber have not been altered themselves. So we have rapid burial in sediment. That's why fossils are found in what kind of rock? Sedimentary rock. And then we will have petrification. We will have petrification and then compaction. These chemical processes will be driven forward by pressure. All right, and compaction occurs when we have multiple sediment layers. What's going to give us multiple sediment layers very rapidly? Anybody have an idea? What's going to give us multiple sediment layers very rapidly? The flood. Okay. So then it could be multiple layers of sediment, and it is certainly accelerated by water, particularly deep water. That provides very high pressure. What's going to provide us very quickly multiple layers of sediment and deep water? The flood. So it's a whole lot easier to explain the fossil record with the Genesis flood than to try to figure out how it can happen gradually. All right, so what is required for fossil formation? There's different processes that can occur in different circumstances depending on what the fossil was buried in, depending on what the original composition of the fossil. There's lots of things that play a role. But what the first thing that is required is rapid burial. Without rapid burial, what happens? We will not have fossil formation. The rapid burial is necessary to prevent decay and scavenging by animals that are going to eat it, or even just the bacteria decomposing it. So we have to have rapid and complete burial or we won't have fossilization. Okay? Next requirement, high rate of sedimentation. That means we have to have a lot of sediment. We need multiple layers of sediment set down. We need the minerals. How are we going to have permineralization, or how are we going to have replacement if we don't have a lot of sediment? We have to have the minerals, and we need the water. The water is going to have to help those minerals infiltrate. The water is necessary for the distillation of our carbon residue fossils. Right? So we have to have rapid burial and a high rate of sedimentation. We also have to have compaction, and this is done through pressure. So we want multiple layers of sediment. We want rapid burial very quickly in multiple layers of sediment, and we want high pressure. So if we don't have rapid burial, we won't get fossilization. We'll have decay and scavenging. If we don't have enough sediment, we won't get fossilization either. We have to have infiltration of minerals. And then we have to have compaction and pressure to drive these chemical processes forward. These three things are required. So we have three requirements for fossilization: rapid burial, a lot of sediment, and high pressure. If one of those is missing, we're not going to get fossilization. We won't get it. So fossilization, does it occur today? Yes, it can if these conditions are met, and they are met. This carbon residue fossil that I showed you, do you think this is millions of years old? Found in shores of Lake Michigan, somewhere in, I don't know if it's Ogden Dunes or Dune Acres, over on the lake shore, not far from here. This is an alewife, okay? It was fossilized if it was buried rapidly, right? It was fossilized if it was buried under adequate layer of sediment and under high enough pressure. Of course, the pressure of Lake Michigan itself. So these are the requirements for fossilization: rapid burial, high rate of sedimentation, and high pressure. Without those, we will not have fossilization. So in summary, what do we know about fossilization? What do you know about it? You need to have an idea of what's involved with fossilization. You need to have an idea of what's going on and why fossils do not prove evolution. Why fossils are a much better testimony to what? The Genesis flood. So what do we know about fossil formation? We know it requires rapid burial. The next thing we know is it can be a complex process, can't it? There's different ways we can have petrification. There's different chemical processes. It could be pre-mineralization, permineralization. It could be replacement. It can be a complex process. We also know that it requires vast amounts of sediment-filled water. We've got to have the water, we've got to have the sediment. Without the water and the sediment, we will not have the permineralization. We won't have the minerals for it. We won't have the water to help infiltrate. We've got to have rapid burial, and we've got to have the sedimentation. We also know that heat or pressure is required. So we need to be buried fairly deeply to get pressure, or we need to be underwater, the pressure of water. So that's what we know about fossilization, fossil formation. What is missing from what we know about fossils? What is missing from the requirements? What's missing? The whole point of this lecture, what's missing? Time. Is time a required ingredient for fossilization? Is it involved in the process? Well, of course it takes time. Anything takes time, but how much time? The answer is we don't know how much time. But I do know it does not take millions and millions of years, especially since we've been finding soft tissue fossil samples where proteins are still recognizable and proteins haven't decayed. Do you think proteins are going to hang around for millions and millions of years? Well, maybe rock can, but not proteins. They've actually found partial red blood cells. Do you think they're going to remain around for 35 million years? Okay, and this nautiloid, 360 million years. The only reason it's dated that way is because it's an invertebrate. That's the only reason, not because we carbon dated it. Do you understand that? The only reason we dated it that old is because we're convinced that evolution occurred, so we're going to put it in our evolutionary scheme. That's the only reason. Okay, so what do we know about fossil formation? Rapid burial. Can be a complicated chemical process, all right? It requires sediment-filled water and pressure, but time is irrelevant. Do you understand that? Time is irrelevant. How long does fossil formation take place? My answer, I guess, would be it depends. Depends on the circumstances. But I do know it does not take millions and millions of years. And what are some reasons that I know that? Well, let's talk about the fossil record. What is in the fossil record? We've talked about this before. I want you to remember it. I want you to understand it and be able to apply it. So what is found in the fossil record? Millions of dead organisms. Millions and millions and millions of dead organisms. Okay? So the fossil record is a testament to death and destruction, isn't it? So we find millions and millions of dead organisms. And the first thing that you think of, well, the first thing that I think about with an organism would be animals. So what kind of animals do we find in the fossil record? We find millions of dead animals. What is in the fossil record? Well, most of the animals in the fossil record are marine invertebrates. What's a marine invertebrate? Well, there's a marine invertebrate, the nautiloids. All right? So 95% of fossil specimen that we have worldwide they are marine invertebrates. All right? Other specimen that we find will be just the bones, the teeth, the shells, or the impressions of animals. We have very few intact organisms. Very, very few intact skeletons. Sue, the T-Rex that the Field Museum has in Chicago, is one of the more complete dinosaur skeletons. Of course, the picture that I showed you, do you think that was the actual skeleton of T-Rex sitting out there in the foyer for everybody to touch? Well, it says don't touch. But do you think they would leave it out in the air and exposed to sunlight and other things? That's a cast. Most of the time you see fossils on display, those are molds and casts of the actual bone. Though at the Field Museum you can see the actual T-Rex head. It's kept in a special case, under special conditions, under certain lighting. All right, but there are very few intact specimens. And most of the intact specimens are like the crab that I showed you and other complete nautiloids and complete shells. They're marine invertebrates. So by far, most of the fossil record is marine invertebrates. Do you remember? They have to explain that away. How do they explain it away? The Cambrian explosion. Do you think all of the marine invertebrates lived at the same time? No, they didn't. Okay, were they buried by the flood? Yes, and they were buried at the bottom because they are smaller organisms. All right, the flood buried things according to habitat. But then how do we get invertebrates and fish and birds and mammals all mixed together? That's a problem for the evolutionary paradigm. We often have different organisms together in mass graves. Of course, we refer to those as fossil graveyards. Fossil graveyards are a problem for evolution to explain. Okay, and so what they have to do is they have to make up a story. Here's a couple examples of fossil graveyards. I don't know how well you can see this. This is masses of bones. This is from it's called the Karoo. It's a area of South Africa. There's all kinds of fossils there. This is also found there. These are a bunch of small juvenile dinosaur bones, all entangled and buried together. What happened? They all fell into the same tar pit at the same time? I guess they were pretty clumsy. That doesn't make sense. All right, so we find millions of dead organisms. Most of the time we think of animals when we think about fossils, but that includes masses and masses of dead plant material. What happened to the plants? How did they get buried? They can't fall into a tar pit or a gravel pit or quicksand. They were buried by the flood. Masses and masses of dead plants. Global flood makes a good explanation. Most of our plant fossils are impressions and carbon residues, because plants don't have bones or teeth or shells and other hard parts that fossilize readily. Our intact plant fossils, of course, would be the petrified wood. Oh, what about the Petrified Forest National Park in Arizona? I've never been there. I'm going to have to get there. That's a problem. Dead plants also are converted to the fossil fuels: oil, coal, petroleum, and natural gas. So the millions of dead organisms that we see in the fossil record includes animal remains, and even more so, masses and masses of dead plant material. That's where we have all the coal that we've been burning and burning and burning and burning. Right? And that's global warming, but we'll talk about that next semester. Okay, here's some pictures from the Petrified Forest National Park in Arizona. There's all kinds of tree trunks laying around. If they just laid around out in the open like that, would they have fossilized? Of course not. Here's one up close. Lots of color. All right. So, what's not in the fossil record? What do we not find? Not found. Oh, but every once in a while, National Geographic and Scientific American and other publications will have a cover issue with, "We found the link between this and that and the other thing." Okay. What are those so-called missing links that are found from time to time and in the news? And then they kind of go away and disappear. Well, they're just an unusual animal. And even at times they've been out and out hoaxes. And the thing about that, evolutionists are very, very hesitant to let people look at the fossil finds. And they don't carbon date them and other things like that. They just don't do it. They're satisfied with their evolutionary paradigm, and that's that. So, transitional forms are not found. Also, what's not in the fossil record? Do we see a nice upward progression of simple to complex? No, we see jumbled fossils all over the place, and in places they probably shouldn't be. Do we see orderly rock layers? Oh, we see nice sedimentation at the Grand Canyon. Well, of course we do, because it was all laid down at the same time. Two views of fossils. Two views. Keep in mind, what is a paradigm? It's a starting point from which scientists reason. So how we view fossils, does it depend on the fossil evidence that we find? Or does it depend on our original presupposition, our paradigm? How do I interpret fossils? I try to look at all the evidence and I try to see what do they really have that convinces them of evolution. And they don't have very much. So the creation paradigm versus the evolution paradigm. The creation paradigm follows what type of geology? Catastrophism. Catastrophism is the view of geology that fits the creation paradigm. Make sure you keep all these things straight. Uniformitarianism is the geology view that fits the evolution paradigm. With the creation paradigm, we're convinced that the Bible is true and that the Genesis flood really happened. Okay? The evolution paradigm is just as convinced. It's just as convinced that creation did not occur, that everything evolved, and so it had to happen by natural processes. Now, keep in mind, what is evolution? I want you to write it down again because I want you to keep this association in your mind. I want you, when you hear the word evolution, I want you to think descent with modification. Evolution can mean a lot of things. It can mean macro or micro. It can mean change. Remember, the word actually means unrolling as a scroll. It can just mean change. Then when you see uniformitarianism, I want you to associate that with the idea of natural processes over geologic time. So what does the word evolution really mean? How is it used? It's used to mean descent with modification. Okay? What does uniformitarianism mean? It's used to mean natural processes over geologic time. Okay? So, if we are a creationist, we're going to view fossil formation how? A catastrophic event facilitated by the Genesis flood. That's how we view fossil formation. If we're an evolutionist, we believe in uniformitarianism. We are going to view fossil formation as gradual processes that occurred during the millions, I don't have enough millions in there, wouldn't fit on the slide, millions and millions of years of Earth history. When you hear the phrase geologic time, it's code for millions and millions and millions of years. Okay, you see the difference? Do you see the contrast? All right. How do creationists use the fossil formation ideas, and how do we use the fossil record? We use it to illustrate stability of species, and we use it to show that the flood is logical. We use it to show that the fossil record would be predicted by the flood. Does that make sense? Are you seeing how this fits together, and why I want you to understand a little bit about fossil formation so you can apply it? As a creationist, the fossil record shows us the stability of species. There's two things that we see overall in the fossil record. We see separate and distinct animals or plants, right? And we see death and destruction. That's the testimony of the fossil record. What about evolutionists? They're going to use strata. They're using fossils as a dating method. Remember, index fossils? And here's my argument, prediction versus accommodation. The fossil record would be predicted by the flood, right? And then the mass graveyards, the petrified forests, those have to be explained away. You see the contrast between the two views. That's the whole point of this lecture. What's the best explanation? by far, had to have a little animation, by far the best explanation for what we see, understand this, write it down. The best explanation for the fossil record is the Genesis flood in two ways. It's the best explanation for fossil formation. Do you understand that? And it's the best explanation for what's in the record itself. Both ideas. The Genesis flood is the best explanation for both fossil formation and the contents of what is found in the fossil record. Remember, I want you to know that Henry Morris, how many times have I bring this up? There's the book. I pulled this slide out of a previous lecture. Henry Morris, in his book, Scientific Creationism, is the one who I saw gave the name to this argument. And I think it's a very good way to argue against evolution. I tell evolutionists, that's in the past. You can't prove it scientifically. So that means as a creationist, I can't prove it either, can I? So I use the prediction versus accommodation argument. Okay? It's Henry Morris's best argument. Look, catastrophism does what? It predicts what's found in the fossil record. It also gives a good way to explain how fossils form. Uniformitarianism has to constantly accommodate. That means they make up stories to try to figure out how those little dinosaurs got all buried together. They make up stories to how dinosaurs became extinct. Okay? So, prediction. Look at all those things predicted by catastrophism. Uniformitarianism. Oh, there are some things that are predicted by the uniformitarianism. So, there are some things that they do have some good points. I don't want you to think that we have all the science on our side. You say, oh, there's some things that don't quite fit the Of course they do. But our understanding can be incomplete. But look at the score. Okay? Stability of species from the Creation Museum. These insects are no different than the ones we have today. There's a mosquito in amber. My question is, if that amber is 35 million years old, why did mosquitoes stop evolving? Okay? Were they already as advanced as they could be? Rapid burial. There's a fish eating another fish. There's all kinds of those fossils. Accommodation. There are some things that we have to explain. We have to explain things. Uniformitarianism. Look at this. Here's a problem. If these layers were laid down gradually, how did that tree trunk get through all those millions and millions of years? Okay. Oh, all right. We will pick up with this later because next lecture is, do you recognize that? The case for catastrophism will be on Monday. We'll see you then.